Good morning, everyone. Good morning.
Good morning. Somebody's having a good day?
Yes, I'm having a great day today.
Happy to hear it.
I might have to leave your class early today, but I'll explain the reason. I'll email you the reason.
Okay, I was about to say. I mean, you could whisper it to me in the chat.
Okay.
Yeah, and that way it's not forgotten. Sorry, in the middle of sending an email while everybody gets in and set up.
Everybody keeps saying here. You're supposed to say here?
You can say something. As long as I have a message with your name on it somewhere in the chat, that's how we've been doing attendance. So always remember to, that's what I mean by sign in. Just say something. Could be a smiley face. As long as it's not like, you know, an F-bomb or something. I know that's what some of you really want to say, but
Oh, shit.
all right. So I like it. Lots of spunk. I like to see people having fun with math class, because I know it's the most riveting thing you guys do all day. All right, so let's see, Shaw. So I've been asked a few questions regarding some random stuff, so I will address that briefly right now. So yes, please make sure to sign in by just putting something in the chat, you know, be something as fun and spunky or sad and quarantine-y as you'd like. Just know, let's keep it PG-13. The next test is going to open on Friday afternoon. We'll be doing our review for it on Friday, but the test is going to be open Friday afternoon through next weekend. So you'll have a week plus some to do it. Same as last time. You'll have, you know, multiple chances and everything like that. So, and I do post these things on YouTube. The YouTube channel information, as well as like my office hours link and WebAssign codes, everything is on the let's see, the e-learning link for this class. Go to e-learning and resources. So the online test overview stuff is right here, and moving online has all of the office hours and class links and everything for like the YouTube stuff. So if you have questions regarding that, that's where it is. Okay. All right. So, so what have we been talking about? What have we been discussing in the class most recently?
What do you call those things with the arrows? Vectors?
Vectors, yeah. And vectors are mathematical objects that have two things. What two things do they have?
Magnitude, direction.
Yep, so they have a magnitude and a direction. There's two different ways of discussing a vector. You can talk about so the symbol for a vector is either, sometimes it's one letter or sometimes it's two letters if you are talking about the two endpoints. But for now, let's just stick with the one. Magnitude, I usually denote by just the letter by itself. And direction is theta, or it could even be theta v. If you have multiple vectors, you might want to distinguish them by putting subscripts telling you who has what angle. But there's another way of describing a vector, different form. And what is that form? Starts with a C.
Scalars.
I'm sorry? I didn't hear what you said.
Can you repeat that question, please?
I'm saying what?
I think they said cumulative.
It's not cumulative. So it's the other way we have of describing a vector. So one of them is magnitude and direction. The other way, which is easier to do math with, is what?
Commutative.
No, that's a property.
Oh, you have component form?
Component form. Yeah. So these are the x, this is the x component and the y component of the vector. All right. So we talked about some different things. You can add these things and you can subtract them, but it's not really subtraction. It is multiplication by a negative and then adding that negative. So the scalar multiplication thing that we talked about, CV is just as simple as this. And this is one of the reasons why we like component form, is if you multiply the vector by some scalar, just a positive or negative number, then the thing you get out, if you try to deal with the magnitudes, we discovered that things get a little weird. I'm sorry, the magnitude and direction, things get weird. But if you do it in component form, it's as simple as this. Multiply the x component times that number and the y component times that number. Okay, so we're going to run through some quick exercises. Let's call it vector A 1, 4 and B okay. So these are our two vectors we're going to deal with. So my question is, what does A minus B equal?
2 minus 2.
2 minus 2. So this is 1, 4 minus B, and you put a negative on there. So what is this plus this?
Negative 2 plus 2.
Negative 2 plus 2, yeah. So this is one vector negative 2, positive 2. So remember, in component form, you just add the x components together and you add the y components, and you get exactly that. 2 or negative 2, 2. What about this one? 2b minus 3a. Well, what is 2b equal?
6 and 4.
Yeah, so 2 times 3 is 6. 2 times 2 is 4. Very good. And what is negative 3a?
Negative 1.
Negative 3, 12.
I'm sorry?
Negative 1 and negative 12.
So I believe negative 12.
I'm sorry.
Negative
Yeah, negative 3. Yeah, okay, very good. So what is 6 plus negative 3?
3.
+3.
+3. And what is 4 plus -12?
-8.
-8. So this is, again, my opinion, the best way to do all of this stuff. Is that think about the components. And in my line of work, which physics is something that I think most of y'all will have to get to, you can play some fun, fancy math tricks whenever you do stuff with vectors, if you're good and really comfortable with it. But the simplest thing to do is generally break something down into its components and then do whatever you're doing, adding, subtracting, multiplying, whatever. Because it's straightforward addition and multiplication. All you have to do is remember that x's go with x's and y's go with y's. At this level, that's as difficult as it gets. But honestly, it's not that involved. It really isn't. So yeah, this is how we do addition, subtraction, and basic scalar multiplication. So let's take these new found operations and introduce them into what we have previously. So when we're asking for the magnitude of V, it looks like this. So this is the technical definition. Sometimes people will get lazy, and by some people I mean me. People who work with vectors a lot, when they do the magnitude, they'll just put 1 bar on each side, because realistically, what do you guys know the 1 straight bar on each side to be? What is that for you guys?
Absolute value.
The absolute value. Yeah. So they use 2 bars because they don't want you to confuse this with the absolute value. But in reality, it makes total sense if you think about it the other way. What is if you just say the magnitude of a vector, what's the equation for the magnitude of a vector?
Can you repeat that?
What is the equation for the magnitude of a vector? So the double lines means take the magnitude of this thing. So what is the equation for the magnitude of a vector?
It's going to be positive. It's going to be equal distance.
So it's the distance formula. It's the length of that vector. What is the distance formula?
Y1 minus Y1.
Okay, so if you're going all the way back, distance between 2 points equals square root of y2 minus y1 squared plus x2 minus x1 squared. I hate this version because it's unnecessarily long. What did I say delta means?
Change.
It's a change in something. So delta y is y2 minus y1. Delta x is x2 minus x1. So delta something just means the value of that thing at some later point minus the starting point. So if you take this version, and this is a big part of why I like this version better, because it keeps this information, but it's shorter to write. And when you're talking about vectors, you don't necessarily know what y1 and y2 are, or x1 and x2. You may not have that information. But what you do have is delta x and delta y, because that's what a vector is. It moves from a starting point, which is x1, y1, to some ending point, x2, y2. So the magnitude is vx squared vy squared. Okay? So the magnitude of something, you square every component and then take the square root of it. Okay? Now, when you go up to 3 dimensions, it's the same idea. It's you just add, we call that the z direction. You just add vz squared. If you go to 4 dimensions, it's vx squared, vy squared, vz squared, v whatever squared. So what about 1 dimension? What if you only had the x direction? Well, the magnitude of a 1-dimensional vector would be square root of vx squared. But what is the square root of a number squared?
1.
Not 1. Let's try, what is the square root of
That number.
5 squared?
Like 2.25.
Now, you were closest with that number. But what's the square root of 5 squared?
5.
What is the square root of negative 5 squared?
Let's say minus 5.
What is negative 5 squared?
25.
What's the square root of 25?
5. Oh,
So the square root of vx squared is the absolute value of vx. So the magnitude of a number is the absolute value of that number. So this is why, one of my little tirades, sorry. They mean the same thing, but a number is just a 1-dimensional vector. So whatever. But for our purposes, this is how you find the magnitude. So let's find the magnitude of our 2 vectors. Let's just say this. I'll do the double lines for now. So what is the magnitude of A?
Square root ax squared plus ay squared.
What is ax?
1,
What is ay?
3,
That sounds right. Which equals what?
10.
I'm sorry?
Square root of 10.
5 and 10.
Yeah.
10.
Yeah. Square root of 10. Because we can't simplify that down anymore. Okay? I mean, you could put it in decimal if you want to, but to me, that's neater than a decimal. What about magnitude of b?
4 squared minus 2 squared. 18. Square root 18.
It's 4 squared.
15.
4 squared is 16,
6.
Minus 4.
which is
12.
12.
everybody okay with that? Because I'm not. I'm sorry?
Simplify to be 2 3.
No. I mean, you could simplify this into 2 squared root of 3, but that's wrong. Why is that wrong?
Is it the square root of 20?
Why is it the square root of 20?
It's
Oh,
negative.
it is. I'll give you that. I'm not trying to mess with you. It is the square root of 20. Why?
Because the negative in the when you subtract and the negative 2 becomes positive.
Because it's not subtraction at all. It's 4 squared plus negative 2 squared. So I'm okay if you shorten your workload down and don't write the parentheses, as long as when you skip that step, you keep it right, because you're squaring everything that's in there. Not just that thing, you're squaring everything else that's in there. Okay, so that's the square root of 20, because this is 16 plus 4. So very good, square root of 20. And can we simplify that at all?
That'd be root 2. I mean, not root 2. 2 by.
Yeah. So this is 2 square root 5. Actually, I'm going to do the in-between steps. So remember, you can split this up into its factors, 4 times 5. And you can consider these two as separate square roots. And then square root of 4 is 2 square root. So yeah, remember, you can simplify it like that. Very good. Okay. What about the magnitude of 2a?
It'll be 4.
It'd be
Plus
4.
It's 36.
Well, what is 2a would be the magnitude of 2 times 1, which is 2. 2 times 3, which is 6. So you do that multiplication. What is the magnitude of that?
The square root of 2 squared plus 6 squared.
Yeah. Sorry, we're running out of room. So what do we get?
Square root 40.
Okay. And can we simplify that at all?
Yeah, the 2 root 10, I think.
I think you are correct. So this becomes 4 times 10. And for the same thing we did last time, you can take out the square root of 4, it just becomes 2. So you get 2 times square root of 10. So scalar multiplication has this interesting property that when you multiply a vector by a scalar and then take its its magnitude, you find that the magnitude of that new thing, which is 2a, is the magnitude of the original thing times that number. So magnitude plays like this. So the magnitude of C times V equals C times the magnitude of V. Except not quite. If I were to take the magnitude of negative 2a, so that's the magnitude of negative 2, negative 6, which equals what?
Positive 4, positive 36.
Exactly. So finish it out. So it's not just the number times the original magnitude, it's actually the absolute value of that thing. An easy way to never mess that up is that magnitudes are always positive, always, until you get into like imaginary numbers, in which case the kind of math you're doing, that'll be probably graduate level stuff if you ever get to that. So you will have learned a couple new tricks by that point, but the same idea applies. So this is what happens when we multiply by a scalar. It only changes the you can't change the sign of the magnitude because it's always positive. But you just get this extra little piece in here. So let's see. I'm going to bring up one last little piece. Okay, so what is the magnitude of vector A?
Nine plus 16.
What is 9 plus 16?
25, right?
It is 25. And what is the square root of 25?
5. No mistake.
All right. So if we were to just look at this, this is a very easy mathematical way to describe all of the magnitude of that vector. But we kind of need a way, a more useful way of describing all of the direction of a vector. So just as a little game, what is A divided by 5 equal to? Don't overthink it.
1.
No, it's not 1.
Is it? Do you take what A is equal to and divide both of them by 5?
Yeah.
Oh, well, it's 3 over 5 and 4 over 5.
Yeah, because we're essentially multiplying it by, if you don't like the dividing thing, you could say that this is 1/5 times that. So my question then is, what is the magnitude of A over 5?
Square root of 3 over 5 squared plus 4 over 5 squared.
So what is 3 over 5 squared?
9 over 25?
9 over 25 plus 4 over 5 squared, which is
16 over 25?
add them together, what do you get?
1.
But I said 1.
Which is why I liked where you were going, but that's not